Hello, we are Team on Semiconductor, and our project is Power Output Driver Automated System for Integrated Circuits Over Time, or POTUS for short. Our technical directors are Frank Kalenko and Robert Davis, both URI graduates. I am Nicholas Amore, an electrical engineering student here. With me today is Robert Robinson, also electrical engineering, Alex Cressman, computer engineering, and Luke Doden, also computer engineering. On Semiconductor is a company located in East Greenwich, Rhode Island, with a headquarters in Phoenix, Arizona. They are a leading supplier of semiconductor solutions with a focus on automotive applications. They develop important parts such as switching regulators, SmartFETs, and relay drivers. Of particular interest to us are the relay drivers. These parts are better known as integrated circuits or ICs. They are a collection of electronic components shrunk down to a tiny chip. ON develops many of these parts as seen here. The part we tested can be seen on the right. When opened up, it can be seen that the actual chip is even smaller, and going further, the actual electronic component is incredibly small. The part we tested can be realized by a simple schematic. The input of the part is the gate connection with protection circuitry. There's an inductive load connected to the output, and the actual output to be tested and monitored. Lastly, there is a diode on each part which we use to monitor temperature, as discussed later. This circuit is repeated 4 to 12 times depending on the part. This is a picture of the current system. There is a socket to hold the part being tested, several output connections, and several input connections. This picture can be realized by the below block diagram. First, the user must set up the board. Then, they must program the function generator, and they must actually send the pulse to the board. They must capture oscilloscope data. From there, if the output does not fail, they must increase the pulse and repeat the steps until the output does in fact fail. When the output fails, they must switch the output, which again could be anywhere from 4 to 12, and once upon all outputs failing, the test is concluded, they have their data, and they can set up the board for another test. The anticipated best outcome of the project is take the following system and fully automate it. There are 3 key features to this. The first is to automate the data extraction. The second is to control the pulse width using a microcontroller. And the third is to design a board that can incorporate all the necessary features into one sleek design. We are happy to say that we met our anticipated best outcome. We were able to take the original system seen on the left and fully automate it with a standalone board to go with it. The impact that this project is going to have is that by fully automating the system, we're going to significantly reduce the amount of time it takes an employee to test a part so they can work on other things instead of consistently manning the system. We're going to drop the amount of time it takes to test parts down from hours to just a couple of minutes. With this freed up time, we can provide additional data as to the parts for important customer parameters. Lastly, there will be significantly less potential for user error. This is a picture of the completed board. It has several key features to it. This is the microcontroller. Here are the OLED display connections, the output switch, the power and safety switch, fail detections, the temperature sensors, and various connection points. This picture has been simplified to a block diagram, which will be discussed in detail throughout the rest of the presentation. The first of which to be discussed is the microcontroller, which will be talked about by Alex Cressman.
The microcontroller, the brains of the PCB board. The microcontroller we used in our case was the Arduino Mega, shown in this image right here. The Arduino was chosen because of its many capabilities and its own programming language, while the Mega was chosen because of its many I/O pins, in which we used most of them. In this picture over here, we see that the Arduino fits nicely on top of the PCB board rather than the bottom, and this was chosen for easy access to the Arduino. The Arduino controls many functions of the PCB board, such as the switching topology and the safety shutoff features. My colleagues will be talking about that in greater detail. We'll all be talking about the signal generating aspect of the Arduino. Now, the Arduino sends a rather unique pulse wave over to the IC, shown in this GIF right here. First, it sends an initial pulse width, then sends incrementing pulse widths all the way up to the maximum pulse width, which is also sent. Now, this pulse wave is created by the user via these onboard push buttons located here. The first set of buttons are the increments in between the initial and maximum pulse width with increase and decrease. The next is the initial pulse width with increase and decrease. The next after that is the maximum pulse width with increase and decrease. Next is the go button. When this is pressed, the user created pulse wave is then sent over to the IC for testing. Next is the board configuration. Currently the board is set to low side configuration, but if the user presses it, it will toggle between high and low side configurations of the board. Next, the Arduino is powered by an external power supply regulated at 9 volts rather than a computer. This was chosen for safety reasons. Now, the Arduino or the microcontroller is located here on this PCB block diagram. Now, when the user inputs the waveform parameters, the parameters are also sent over to the OLED displays, so they can be updated in real time of what the user is inputting. So in this example right here, we have the programming screen, and the initial pulse width is 10 milliseconds. The increment is 5 milliseconds, and the maximum is 30 milliseconds. So if the user presses go at this point, it will send a pulse width of 10 milliseconds, 15 milliseconds, 20 milliseconds, all the way up to 30 milliseconds. In this next screen over here, we have the testing results. Currently, the board is set for a low side configuration. The current pulse width is 10 milliseconds, and this final bit of data tells whether or not the test is finished. In this case, the test was finished. Now, with the OLED displays out of the way, the Arduino also communicates over to the switching topology and the safety shutoff feature, which Robert Robinson will be talking about in greater detail.
A concern for the functionality of a board is the automation of switching between outputs of the IC one at a time. In order to accomplish this, we ultimately decided to use electromechanical relays for the design of our output switching topology. We repeated this topology 12 times in order to accommodate ICs that have up to 12 output pins. The relays are triggered when 5 volts are applied to the relay coil. An NMOS disrupts the connection between 5 volts and ground to prevent premature triggering of the relays, opening and completing the connection to ground once a pulse is sent to the NMOS from the Arduino. The diode and resistor serves additional safety features, namely flat black protection and assurance the coil won't be triggered prematurely, respectively. While this configuration allows us to switch between outputs automatically and safely, we must also contend with how the fail conditions of the ICs under test may affect the board. A safety issue due to the nature of the ICs we're testing is that ICs often fail in a short condition. Some sort of safeguard is necessary to minimize the risk of too much current flowing directly into the board and subsequently damaging it, so we implemented a safety switch. The safety switch is comprised of an NMOS cascaded with a PMOS. The NMOS receives a pulse from the Arduino, which turns the PMOS on. When the pulse time ends, the PMOS and NMOS are turned off, which disconnects the battery voltage, the BAT, from the inductor, which will then safely discharge the remainder of its current through the system. While our safety shutoff and switching topology were adequate for our prototype, we also decided it was necessary to add some additional features, namely a temperature sensor and fail detection system. A consideration we overlooked with our prototype is that pulse widths continue to increase when attempting to damage a pin, but the delay between pulses always remain the same. The consequence for the temperature continuing to ramp up is that parts may fail earlier at higher temperatures, leading to inaccurate data. To remedy this, we developed a temperature sensor. The Arduino sends a pulse to the NMOS, which then closes the PMOS, causing the 5-volt source to connect to the input of the NMOS current mirror. This NMOS current mirror allows current to flow through the body diode of the IC we're testing by putting a negative polarity on the drain pin. We also need an amplifier for this to work properly. This is because the diode voltage is being monitored by the ADC on the Arduino, which is referenced by 5 volts. The maximum voltage drop across the typical silicon diode is about 0.6 volts, so we need to amplify this value so the Arduino can read it properly. We use an inverting op-amp to solve this issue, as the drop of the Arduino is reading is also a negative value. We designed this part to have a gain of about 8, which lets the Arduino detect the amplified voltage drop. For our prototype, we had the idea of using code to look through data automatically to determine failure points. This proved to be inefficient, however, so we created a fail detection circuit. For this design, we added a PMOS in series with an NMOS to serve as an enable for the PMOS pulled to 5 volts. This is done to prevent premature readings of failures. The PMOS pulled to 5 volts itself is controlled at its gate by the output MOSFET of the IC. The Arduino monitors the 10K resistor connected to ground, which is held low when the PMOS is turned off. As the PMOS is triggered when the drain pin on the output MOSFET is pulled low, A failure is signaled when the PMOS turns on and connects 5 volts to the resistor being monitored. As the drain pin can see as much as 40 volts, a safeguard in the form of a simple voltage divider was used to step down the voltage of the gate of the PMOS to around 8 volts. All the features previously discussed were designed for low-side configuration. We decided that high-side support for a board which the user can swap between via jumpers. Implementing this was simply a matter of rearranging components. The high and low side variations of a feature function identically. With these hardware features out of the way, Luke Thoden will discuss the role our oscilloscope played in this project and how we took advantage of it.
The system uses a Teledyne LaCroix oscilloscope to capture the device's output voltage, output current, output energy, and input pulse. For our purposes, we're concerned with current and energy. We'd like to extract this data, and we did so previously using ActiveDSO with Visual Basic for applications within Excel to sweep cursors across the current and energy waveforms and plot them in Excel. The problem with this is that sweeping the cursors took way too long and required a PC. Since we're no longer using a PC, we had to use a different method. The method we chose was to use the oscilloscope's autosave feature, which saves CSVs of every waveform with every pulse. In order to analyze this data, we created a Python application. The user is provided with a Capstone flash drive that is plugged into the oscilloscope, and as soon as they run the capstone.py script, a command window will open. After this finishes running, a GUI will open, and the user has the option of graphing any of these CSVs. I will now give a video demonstration of how the program works. After the user finishes testing a device, on the oscilloscope, they are to navigate to the Capstone flash drive. This will contain the necessary folders and files needed to run the application. The autosave folder will contain all the waveforms in CSV form saved during the test. We have the copied folder, WinPython, which contains all the necessary Python libraries in order to run the application, and capstone.py. The user will click on capstone.py and a command window will open up. This will ask the user to input the path of where the waveforms were saved. This is the autosave folder. Upon hitting enter, the program will run. This will output the CSVs where the device failed for current and energy, along with the peaks of each of those waveforms. After the command window is done running, a GUI will open up. This will show the max current of the entire test, max energy of the entire test, and will allow the user to graph. If I were to click Show Current Graph, another window will open up and ask me to select file to graph for current. I'll have to choose the CSV I want to graph. So say I wanted to graph CSV 3. I can type in 3 and hit graph. This also allows me to plot two waveforms on one. So if I wanted to compare CSV 3 and CSV 8, I'm able to do that. Lastly, the CSVs where the device failed will be stored over in the copied folder. With all these features realized, we're able to take an initial block diagram and transform it into a fully functional system and achieve our anticipated best outcome. And with that, I'd like to give a huge thank you to everyone that helped us with our project. Our technical directors, Frank Kolenko and Robert Davis, on Semiconductor employees, Jordan Beauclair and Eric Moberg, our consulting technical director, Alex DiPetrillo, and of course, Dr. Harish Sunak, our Capstone program director. Thank you.